A fire control system is a number of components working together, usually a gun data computer, a director, and radar, which is designed to assist a weapon system in hitting its target. It performs the same task as a human gunner firing a weapon, but attempts to do so faster and more accurately. Naval fire control. The original fire control systems were developed for ships. The early history of naval fire control was dominated by the engagement of targets within visual range. In fact, most naval engagements before 1800 were conducted at ranges of 20 to 50 yards. Even during the American Civil War, the famous engagement between the US Monitor and the CSS Virginia was often conducted at less than 100 yards range. Rapid technical improvements in the late 19th century greatly increased the range at which gunfire was possible. Rifled guns of much larger size firing explosive shells of lighter relative weight so greatly increased the range of the guns that the main problem became aiming them while the ship was moving on the waves. This problem was solved with the introduction of the gyroscope, which corrected this motion and provided sub-degree accuracies. Guns were now free to grow to any size, and quickly surpassed 10 inches caliber by the turn of the century. These guns were capable of such great range that the primary limitation was seeing the target, leading to the use of high masts on ships. Another technical improvement was the introduction of the steam turbine, which greatly increased the performance of the ships. Earlier screw-powered capital ships were capable of perhaps 16 knots, but the first large turbine ships were capable of over 20 knots. Combined with the long range of the guns, this meant that the ships moved a considerable distance, several ship lengths, between the time the shells were fired and landed. One could no longer eyeball the aim with any hope of accuracy. Moreover, in naval engagements it is also necessary to control the firing of several guns at once. Naval gunfire control potentially involves 3 levels of complexity. Local control originated with primitive gun installations aimed by the individual gun crews. Director control aims all guns on the ship at a single target. Coordinated gunfire from a formation of ships at a single target was a focus of battleship fleet operations. Corrections are made for surface wind velocity, firing ship roll and pitch, powder magazine temperature, drift of rifled projectiles, individual gun bore diameter adjusted for shot-to-shot enlargement, and rate of change of range with additional modifications to the firing solution based upon the observation of preceding shots. The resulting directions, known as a firing solution, would then be fed back out to the turrets for laying. If the rounds missed, an observer could work out how far they missed by and in which direction, and this information could be fed back into the computer along with any changes in the rest of the information and another shot attempted. At first, the guns were aimed using the technique of artillery spotting. It involved firing a gun at the target, observing the projectile's point of impact, and correcting the aim based on where the shell was observed to land, which became more and more difficult as the range of the gun increased. Between the American Civil War and 1905, numerous small improvements, such as telescopic sights and optical rangefinders, were made in fire control. There were also procedural improvements, like the use of plotting boards to manually predict the position of a ship during an engagement. Then increasingly sophisticated mechanical calculators were employed for proper gun laying, typically with various spotters and distance measures being sent to a central plotting station deep within the ship. There the fire direction teams fed in the location, speed and direction of the ship and its target, as well as various adjustments for Coriolis effect, weather effects on the air, and other adjustments. Around 1905, mechanical fire control aids began to become available, such as the Dreyer table, Du-Maresque, and Argo clock. But these devices took a number of years to become widely deployed. These devices were early forms of rangekeepers. Arthur Pollin and Frederick Charles Dreyer independently developed the first such systems. Pollen began working on the problem after noting the poor accuracy of naval artillery of gunnery practice near Malta in 1900. Lord Kelvin, widely regarded as Britain's leading scientist, first proposed using an analog computer to solve the equations which arise from the relative motion of the ships engaged in the battle and the time delay in the flight of the shell to calculate the required trajectory and therefore the direction and elevation of the guns. Pollen aimed to produce a combined mechanical computer and automatic plot of ranges and rates for use in centralized fire control. To obtain accurate data of the target's position and relative motion, Pollen developed a plotting unit to capture this data. To this he added a gyroscope to allow for the yaw of the firing ship. Like the plotter, the primitive gyroscope of the time required substantial development to provide continuous and reliable guidance. Although the trials in 1905 and 1906 were unsuccessful, they showed promise. Pollen was encouraged in his efforts by the rapidly rising figure of Admiral Jackie Fisher, Admiral Arthur Knevet Wilson and the Director of Naval Ordnance and Torpedoes, John Jellicoe. Pollen continued his work, with occasional tests carried out on Royal Navy warships. Meanwhile, a group led by Dreyer designed a similar system. Although both systems were ordered for new and existing ships of the Royal Navy, the Dreyer system eventually found most favor with the Navy in its definitive Mark IV* form. The addition of direct-to-control facilitated a full, practicable fire control system for World War I ships, and most RN capital ships were so fitted by mid-1916. The director was high up over the ship where operators had a superior view over any gun layer in the turrets. It was also able to coordinate the fire of the turrets so that their combined fire worked together. This improved aiming and larger optical rangefinders improved the estimate of the enemy's position at the time of firing. The system was eventually replaced by the improved Admiralty Fire Control Table for ships built after 1927. During their long service life, rangekeepers were updated often as technology advanced, and by World War II they were a critical part of an integrated fire control system. The incorporation of radar into the fire control system early in World War II provided ships the ability to conduct effective gunfire operations at long range in poor weather and at night. For U.S. Navy gunfire control systems, see Ship Gunfire Control Systems. The use of direct-to-controlled firing, together with the fire control computer, removed the control of the gun laying from the individual turrets to a central position, although individual gun mounts and multi-gun turrets would retain a local control option for use when battle damage limited direct-to-information transfer. Guns could then be fired in planned salvos, with each gun giving a slightly different trajectory. Dispersion of shock caused by differences in individual guns, individual projectiles, powder ignition sequences, and transient distortion of ship structure was undesirably large at typical naval engagement ranges. Directors high on the superstructure had a better view of the enemy than a turret-mounted sight, and the crew operating them were distant from the sound and shock of the guns. Gun directors were topmost, and the ends of their optical rangefinders protruded from their sides, giving them a distinctive appearance. Unmeasured and uncontrollable ballistic factors, like high altitude temperature, humidity, barometric pressure, wind direction and velocity, required final adjustment through observation of the fall of shot. Visual range measurement was difficult prior to availability of radar. The British favoured coincident rangefinders while the Germans favoured the stereoscopic type. The former were less able to range on an indistinct target but easier on the operator over a long period of use, the latter the reverse. Submarines were also equipped with fire control computers for the same reasons, but their problem was even more pronounced. In a typical shot, the torpedo would take 1 to 2 minutes to reach its target. Calculating the proper lead, given the relative motion of the two vessels, was very difficult. and torpedo data computers were added to dramatically improve the speed of these calculations. In a typical World War II British ship, the fire control system connected the individual gun turrets to the director tower and the analog computer in the heart of the ship. In the director tower, operators trained their telescopes on the target. One telescope measured elevation and the other bearing. Rangefinder telescopes on a separate mounting measured the distance to the target. These measurements were converted by the fire control table into the bearings and elevations for the guns to fire upon. In the turrets, the gun layers adjusted the elevation of their guns to match an indicator for the elevation transmitted from the fire control table. A turret layer did the same for bearing. When the guns were on target, they were centrally fired. Even with as much mechanization of the process, it still required a large human element. The transmitting station for HMS Hood's main guns housed 27 crew. Directors were largely unprotected from enemy fire. It was difficult to put much weight of armor so high up on the ship, and even if the armor did stop a shot, the impact alone would likely knock the instruments out of alignment. Sufficient armor to protect from smaller shells and fragments from hits to other parts of the ship was the limit. The performance of the analog computers was impressive. The battleship USS North Carolina during a 1945 test was able to maintain an accurate firing solution on a target during a series of high-speed turns. It is a major advantage for a warship to be able to maneuver while engaging a target. Night naval engagements at long range became feasible when radar data could be input to the rangekeeper. The effectiveness of this combination was demonstrated in November 1942 at the Third Battle of Savo Island when the USS Washington engaged the Japanese battleship Kirishima at a range of 8,400 yards at night. The Kirishima was set aflame, suffered a number of explosions, and was scuttled by her crew. She had been hit by 9 16-inch rounds out of 75 fired. The wreck of the Kirishima was discovered in 1992 and showed that the entire bow section of the ship was missing. The Japanese during World War II did not develop radar or automated fire control to the level of the U.S. Navy and were at a significant disadvantage. By the 1950s, gun turrets were increasingly unmanned, with gun laying controlled remotely from the ship's control center using inputs from radar and other sources. The last combat action for the analog rangekeepers, at least for the U.S. Navy, was in the 1991 Persian Gulf War when the rangekeepers on the Iowa-class battleships directed their last rounds in combat. Coast Artillery Fire Control. In the United States, coast artillery fire control systems began to be developed at the end of the 19th century and progressed on through World War II. Early systems made use of multiple observation or base end stations to find and track targets attacking American harbors. Data from these stations were then passed to plotting rooms, where analog mechanical devices, such as the plotting board, were used to estimate targets' positions and derive firing data for batteries of coastal guns assigned to interdict them. U.S. coast artillery forts bristled with a variety of armament, ranging from 12-inch coast defense mortars, through 3-inch and 6-inch mid-range artillery, to the larger guns, which included 10-inch and 12-inch barbette and disappearing carriage guns, 14-inch railroad artillery, and 16-inch cannon installed just prior to and up through World War II. Fire control in the coast artillery became more and more sophisticated in terms of correcting firing data for such factors as weather conditions, the condition of powder used, or the Earth's rotation. Provisions were also made for adjusting firing data for the observed fall of shells, as shown in the figure at right. All of these data were fed back to the plotting rooms on a finely tuned schedule controlled by a system of time interval bells that rang throughout each harbor defense system. It was only later in World War II that electromechanical gun data computers, connected to coast defense radars, began to replace optical observation and manual plotting methods in controlling coast artillery. Even then, the manual methods were retained as a backup through the end of the war. Anti-aircraft fire control. By the start of World War II, aircraft altitude performance had increased so much that anti-aircraft guns had similar predictive problems, and were increasingly equipped with fire control computers. The main difference between these systems and the ones on ships was size and speed. The early versions of the High-Angle Control System, or HACS, of Britain's Royal Navy were examples of a system that predicted based upon the assumption that target speed, direction, and altitude would remain constant during the prediction cycle, which consisted of the time to fuse the shell and the time of flight of the shell to the target. The USN Mk-37 system made similar assumptions except that it could predict assuming a constant rate of altitude change. The Kerrison predictor is an example of a system that was built to solve laying in real time, simply by pointing the director at the target and then aiming the gun at a pointer it directed. It was also deliberately designed to be small and light, in order to allow it to be easily moved along with the guns it served. The radar-based M9-584 Seychelles Rupees anti-aircraft system was used to direct air defense artillery since 1943. The MIT Radiation Labs -584 Seychelles Rupees was the first radar system with automatic following. Bell Laboratories M9 was an electronic analog fire control computer that replaced complicated and difficult-to-manufacture mechanical computers. In combination with the VT proximity fuse, this system accomplished the astonishing feat of shooting down V-1 cruise missiles with less than 100 shells per plane. This system was instrumental in the defense of London and Antwerp against the V-1. Aircraft-based fire control. World War II bomb sights. An early use of fire control systems was in bomber aircraft, with the use of computing bomb sights that accepted altitude and airspeed information to predict and display the impact point of a bomb released at that time. The best-known United States device was the Norden bomb sight. World War II aerial gunnery sight. Simple systems, known as lead computing sights, also made their appearance inside aircraft late in the war as gyro gun sights. These devices used a gyroscope to measure turn rates, and moved the gun sight's aim point to take this into account, with the aim point presented through a reflector sight. The only manual input to the sight was the target distance, which was typically handled by dialing in the size of the target's wingspan at some known range. Small radar units were added in the post-war period to automate even this input, but it was some time before they were fast enough to make the pilots completely happy with them. Post-World War II systems. By the start of the Vietnam War, a new computerized bombing predictor, called the Low-Altitude Bombing System, began to be integrated into the systems of aircraft equipped to carry nuclear armaments. This new bomb computer was revolutionary in that the release command for the bomb was given by the computer, not the pilot. The pilot designated the target using the radar or other targeting system, then consented to release the weapon, and the computer then did so at a calculated release point some seconds later. This is very different from previous systems, which, though they had also become computerized, still calculated an impact point, showing where the bomb would fall if the bomb were released at that moment. The key advantage is that the weapon can be released accurately even when the plane is maneuvering. Most bomb sights until this time required that the plane maintain a constant attitude, though dive bombing sights were also common. The LABS system was originally designed to facilitate a tactic called toss bombing, to allow the aircraft to remain out of range of a weapon's blast radius. The principle of calculating the release point, however, was eventually integrated into the fire control computers of later bombers and strike aircraft, allowing level dive and toss bombing. In addition, as the fire control computer became integrated with ordnance systems, The computer can take the flight characteristics of the weapon to be launched into account.